Okay, so now let's discuss the center mass of a rigid body with uniform density but in 3D. We have discussed in the past the 1D, 2Ds, and now we're in 3D. So this question says, find the center mass of a uniform hemisphere with radius r, and the density of the hemisphere is rho. So how do you find this? Well, first of all, let's review how to do this in 2Ds or less. So first of all, you need to look at the symmetry. So in the 2D example, so let's just draw. I had this 2D example in a previous video. This is half of a disk. It's a solid disk. So if I drew it symmetrically enough, I know that the center mass should lie along this symmetry axis, right, somewhere here, and according to our answer in that previous video, somewhere over here, almost 1/3 of the way from the bottom. So in the hemisphere, what do we expect? So we have this hemisphere, and it has this symmetrical axis through the center to the center of the larger circle on the bottom. So the center mass must lie along this body radius, this line here, right? So that is the symmetry argument. So I should set up my axis along this direction, and in my convention, I would like to do x and y and a z. All right, so now the way to cut the object into slices, we had this object, we were cutting it into slices like that, and these slices will be able to stack up into this half disk. And I was calculating the area of the slice to find out its mass, right? So that was how I was able to do it. I had each slice and its vertical coordinate, and then also its area that turns into a mass. So in order to make a similar operation here, I need to cut it into these, instead of these slices that look like bars, I'll slice this into discs, right? So I'll slice it something like this, right? I'll slice something like that, right? So if I slice the whole hemisphere, I can have multiple slices. Each slice is a disk that has a center mass exactly going along this symmetrical axis now we have at z. So we're going to look at this slice and find out how much mass is in the slice. Now this slice is a small volume. Alright, so let's move on to the left side so I can draw a bigger diagram. This is just for comparison, what we were doing and what we're going to do now. So let's see if I can still draw a circle. Let's see, 2, 3. Let's do this. 1, 2, 3. Okay. Well, good enough. Okay, so here's our hemisphere, and we have our z-axis. So x-axis with some perspective, y-axis, and we're slicing. So right here, and by the way, the slice doesn't really look like a disc. If you look at the edge of this slice very carefully, just think about slicing an onion. The onion rings don't really look like regular ring shapes. They have this curvature, but that is what we're willing to ignore. The reason is we can slice this so finely that each slice is as thin as a piece of paper. So can you still see this this curvature here with one thin piece of paper? You probably can't, right? So as long as we can approach that kind of slicing with slicing infinitesimally thin slices, the shape basically just approaches a disc in theory. So let's put a point here. This is supposed to be the center of this disk, and it should have a coordinate called z. So the center of that disk. And we'll also draw this line here. So from the center, this is the origin, from the center of the hemisphere to any point on the surface, we have radius r. And from the center of this disk, going to the side, we have this radius. Let's use lowercase r. I reserve uppercases for constants, and lowercases are variables. This is actually lowercase z. So basically, in this right angle triangle, we have the height z, we have a fixed hemisphere radius r, we also have this variable radius lowercase r. So if you imagine moving to a different slice, say if you move down, the z will actually get less. This r will have a shallower angle, but it doesn't change length. And this horizontal lowercase r, on the other hand, will get longer, right? So if we go to a higher z value, say right here, and the small radius will get smaller, the lowercase r. The large circle's radius doesn't change, and the z gets higher. So there's this relationship among all these three variables, and it's useful to find these relationships so we can later do some variable substitution. So I'm going to look at this right angle triangle. I'll draw it over here. Okay. Alright, so this vertical side is z, and this is r, this is lowercase r. So we just realize the relationship is r squared equals lowercase r squared plus z squared, right? So if you want to find out the mass of this slice, you need to find the volume of the slice, right? And to find the volume of the slice, assuming it is a disk, we need to know the thickness, which we can call delta z, and also the cross-sectional area, which is pi lowercase r squared. So we need this lowercase r, right? Actually, we'd rather just need this lowercase r squared, right? So lowercase r squared, according to Pythagorean theorem, is uppercase r squared minus z squared. All right, we're going to need that. All right, so let me mark on the diagram the thickness of the disk is called the delta z. Okay, so delta z will approach 0 in our integral. And now let's calculate how much mass is included in the slice. We call it delta m. And assuming the slice is a disk, so it should be the thickness times the cross-sectional area. So it is thickness, cross-sectional area, let's use A, and then multiply by the density. So this whole thing is the volume, and this is the volumetric density, so kilogram per volume per cubic meter. So times the volume gets you back to the mass. So delta z stays delta z. Area pi r squared. This is that lowercase r squared. We're talking about, we're talking about this slice. So the slice changes radius as you go to a different slice. So this pi r squared times the rho. And we can use this to replace r squared. And our delta m is equal to delta z pi rho capital R squared minus z squared. Let's remove that and make a longer subtraction. Okay. All right. So now we can take the limit of delta z going to 0. So we're going to very thinly slice our disk, our hemisphere. And so let's take limit of this delta m when delta z approaches 0. So now we should have an infinitesimally small amount of mass, only dm. And over here, everything stays finite except for the thickness of the slice. That turns into dz. Let's put dz on the right side. That is our convention, mathematical convention here. Okay, so what I just worked out is very important. dm appears in our integrations for center of mass, and dm cannot be calculated without getting dm into a coordinate. So now I turn dm into dz and some functions of z, right? So now I can do my integration. So this is how important it is to work out how to turn the mass differential quantity into a position or length differential quantity. So once you have that, you're halfway from getting finished up. So now, because the coordinate I selected is z, I forgot to put the z here. So I'll calculate the center of mass in the z direction. The center of mass in x and y directions are both 0. So we're going through this symmetrical axis, right? It's along this axis where it's x and y coordinates are both 0. So there's just a z coordinate. And this is equal to, so z dm over the integral of dm. Right, so dm, we just figured out dm is equal to this whole thing. So we'll do the bottom, we'll do the top, and we'll combine them. And for the bottom, there's a trick. The total mass of a hemisphere. So if you know the total volume of a hemisphere, and then multiply that with the volumetric density here, and then you get total mass. So you don't have to calculate this by integration, unless somehow this is a shape you don't really know how to calculate volume for, or somehow this density is not a constant. Unless those situations apply, you can just go ahead and find out the volume and multiply the volume with density. So let's do that. Let's say mass total equals integration of dm, which is equal to volumetric density times volume of that hemisphere. So you can check your Google sources or just check your memory. This is half the volume of a sphere, right? So the sphere's volume is 4/3 pi r cubed. This is only 2/3, right? 2/3 pi r cubed. Remember, this is a capital R, right? Capital R is that fixed radius. The lowercase r is changing with the slice. Okay, so now we have this. This is a total mass. Looks like a lot, but it will divide out. If you have watched my previous video on this half disk, a lot of things actually canceled out. Alright, so let's move on to calculate the top integral. So the top integral, z dm, is equal to z, and the dm gets replaced, right? So the dm gets replaced by the whole thing. So let's make sure we are not missing any factors. Pi rho r squared minus z squared, parentheses, dz. And now we also have an opportunity to indicate these limits or the bounds. So in order for the slices to make up a whole hemisphere, the slices must start from 0z and go all the way up to this top apex. So that is r. So z goes from 0 to r. And well, if you wish to find out the center mass of a whole sphere, you can go from minus r to r, and you'll find out the integral is going to give you 0, because you know where that whole sphere's center mass is located. Its exact center, right? Or if you want to find out the center mass of a sphere, maybe with a piece cut out, so you can go from that position all the way up to this, right? So the shape is really determined by the geometry here that we were exploiting right here, and also is determined by these bounds. So by saying from 0 to r, you're doing a hemisphere. You can do other shapes as well. So if you do just maybe a portion of this hemisphere starting from maybe half r to whole r, you can do that too if you want. The formula is going to be exactly the same, just changing this value, right? It doesn't even affect the integration. So all different tricks here, right? Okay, so back to the integration. What are we integrating? We have these constants, right? So constants come out, and we'll ignore these limits now and just write zr squared minus z cubed dz. So we can separately integrate these two terms. Each one is a polynomial. Z squared, well, actually, I think I swapped the, actually, you know what, this is correct. And z times r squared, so z integrates into half z squared and times r squared, and then z cubed integrates into 1/4 of z to the fourth power with a negative in front, right? So each term can be easily integrated. So let's go ahead and get these integrations written out. Where does that go? Here. Okay, so I'm going to integrate these two terms. So pi rho r squared z squared over 2 minus z fourth power over 4. And they're going to be evaluated between 0 and r. I can ignore the 0. 0 will make both terms equal to 0. And just plug in the r. So here we have r squared over 2. So it's half r to the fourth power minus r to the fourth power, well, a quarter of that. So half minus a quarter, that gets you a quarter left. So I'll have pi rho r fourth power over 4. So that is the numerator. And let's combine the two, denominator and numerator, in order to get our z center mass. So let's start the next line. So z center of mass is equal to, so this top here, pi rho r to the fourth power, and divide by 4. Let's just put the 4 in the denominator, and then divide by this. I'll have rho, I have a 2, I have a pi, I have r cubed, and that's 1/3. You can just bump it up to the top. Okay, good. So let's divide out some common factors. Pi's are gone, rho's are gone. R to the third power divides out r to the third power, so we have this r left. And that makes sense because r carries the unit, and the center mass z is a length unit, and being proportional to another length unit makes complete sense. It cannot be proportional to length squared, right? The units won't match. So we have 3r over, so 2 and 4, so 3/8 of an r. So it's a bit lower than half the r. So if you go to the half r, I'm pretty sure the top half has less mass than the bottom half, so you're not exactly balanced. So you want to go down a little bit until you get to 3/8 from the bottom. That's where your center of mass is. So somewhere over here. Thank you.